Okay, so welcome back to this next video in which we are discussing drug addiction. Okay, so we've discussed that the property of all addictive drugs is that they increase dopaminergic transmission in the nucleus accumbens and medial prefrontal cortex. Okay, and that this underlies their addictive properties and how they can induce intense cravings and wantings that can become so powerful that they dominate over every other life aim that the person previously had. Okay, and how also they lead to these intense associations between drug-associated cues and then the drug-seeking behavior, and that these associations can become so strong that they almost displace voluntary control of behavior, so that when you see a drug-associated cue, you begin the drug-seeking behavior without voluntary agreeing to that. Okay, so we've now seen how cocaine does this, okay, by blocking the dopamine transporter and thereby leaving the dopamine in the extracellular fluid so that it can act on receptors on the postsynaptic neurons more, okay, and that's effectively the equivalent of activating the ventral tegmental area, because all activating the ventral tegmental area does is result in an increase in the amount of dopamine that's being released into the nucleus accumbens and the medial prefrontal cortex. So by blocking the reuptake, you're exaggerating the basal amount of dopamine that was being released so that it now becomes a bigger effect. Okay, right. Now we're going to discuss the amphetamines. Okay, now the mechanism of the amphetamines is a little bit more complicated. Now, firstly, we can talk about something that is completely agreed on, which is the different types of amphetamines. Okay, so basically, amphetamines is a broad class, okay, but there are three that I'm going to talk about, okay, and they all work, well, they're all believed to work in the same way, or at least they're all believed to cause addiction in the same way. Okay, so, amphetamines then. The three amphetamines that we are going to discuss is amphetamine itself, okay? So I'll firstly show you the structure of amphetamine itself, then we'll look at methamphetamine as well, and finally we'll look at MDMA. Okay, right, so amphetamine then, okay? So firstly we'll draw the benzene ring. So here, this is a benzene ring here, so I'll have alternating double and single bonds. Okay, now I'll draw a skeletal structure for amphetamines. So remember, in skeletal structures, you don't show carbon atoms, they're implicitly shown by corners. Okay, and you don't show hydrogen atoms coming off carbon atoms either, where you've got missing bonds. So for instance, all of these 6 carbons have a single missing bond, okay? All carbon atoms should have 4 bonds. They've only got 3. So where there are missing bonds, that's implicitly to a hydrogen. Okay, then you'll have a carbon here, okay, another carbon here, okay, and then off this carbon you're going to have an amino group here, okay, and then you're also going to have a methyl group like so. That is the structure then of amphetamine. Okay, so amphetamine itself is a molecule. This is the structure of that molecule, okay, but the broader class of amphetamines, all of the molecules in this broader class of drugs all have a similar structure to amphetamine itself. Okay, hence why they're called amphetamines. Okay, so let's now see the related structure of methamphetamine. Okay, oh, and by the way, amphetamine is often abbreviated just to AMPH. Okay, the first 4 letters are of amphetamine. Okay, methamphetamine then. Okay, which is often just abbreviated to meth for short, the first 4 letters of its name. Okay, so methamphetamine is exactly the same structure as amphetamine, but you have an additional methyl group coming off it. So let's show this. So firstly we'll draw our benzene ring again. Okay, so this is exactly the same between both amphetamine and methamphetamine. Okay, then you're going to have the 2 carbons here and here again. Okay, you'll have the 3rd carbon going off there, then you'll have this amino group, but now off this amino group you're going to have a methyl group like so. Okay, so skeletal structures always look a bit odd when you put methyl groups like this, because all you need to do is now show a line to a point down here, and then this point represents a carbon atom, and then the fact that it's got no more bonds on it indicates to us that all the other bonds are to hydrogen atoms. Okay, and hence that's a methyl group. Okay, this is a methyl group down here as well. Okay, so that's methamphetamine. Okay, the final one I want to show you is MDMA, and I think I'll try and squeeze this in on this same page, so I'll put it up here. Okay, so the final one is known as MDMA, okay, which is short for, okay, it's a long name, whoops, missed off the first bit, okay, methylene, okay, that's the first M, okay, and then it's methylene dioxy, so methylene dioxy, and then the MA is for methamphetamine. Now ideally it would have all been one word, okay, but because of lack of space I can't write it as all one word, so this should have been connected to this. Methylene dioxy methamphetamine then. Okay, now it has a more common name. It's more commonly known as ecstasy. Okay, so let's see the structure of ecstasy then. So it's methamphetamine with a little bit more added onto it, with this methylene dioxy portion added onto it. So let's start by redrawing the structure of methamphetamine. Okay, so here is our benzene ring, once again here. Okay, like so. Okay, and then here is the two carbons here, okay, with the nitrogen atom here. Okay, a hydrogen coming off that nitrogen atom and the methyl group of methamphetamine, and then that methyl group there that was on the original amphetamine. Okay, now what we're going to do is put two oxygens coming off this carbon and this carbon, like so, and we're going to have a methylene group in between them. So remember, a methylene group is just a carbon with two hydrogens coming off. This was a methylene group here. Okay, this is our methylene group here. Okay, like so, and then the methylene group is in between two oxygens, so that's the methylene dioxy here. Okay, so you really have just attached methylene dioxy onto methamphetamine, and that's why it's called methylene dioxy methamphetamine, or MDMA for short. Okay, M for methylene, D for dioxy, M for meth, and then A for amphetamine. Okay, right, so then what are all these different drugs going to be doing? Well, they're all going to cause dopamine release by dopaminergic neurons, and they're going to do it in a way that doesn't require action potentials. Okay, so they are going to go into the axon terminals of dopaminergic neurons, and they cause them to release dopamine even when there is no action potential arriving. Okay, and the way that they cause the release of dopamine does not involve the fusion of the synaptic vesicles with the membrane as it would if an action potential arrived. Okay, so basically the amphetamines work on the axon terminals, and the axon terminals start releasing loads of dopamine spontaneously. Okay, but it's not through the fusion of vesicles with the presynaptic membrane. It works by a different route. Now, the mechanism, the exact mechanism by which these work is still controversial. If you read different papers on this, you'll get different answers, basically. Okay, the problem is that loads of people have kind of got contradictory results with this. Okay, but I'm going to give you a picture, regardless of what I think the general viewpoint is as to how these things work. Okay, if you want to take the risk-free approach to this, then just learn the fact that if you put amphetamines on axon terminals of dopaminergic neurons, these dopaminergic neuron axon terminals will release loads of dopamine, basically, okay, without action potentials and without fusing the vesicles with the cell membrane. Okay, that portion is incontrovertible, we know that. Okay, what I'm about to tell you is a little bit more controversial. Okay, so I think the general viewpoint of how these drugs work is that they set up this, what's known as a reverse transport mechanism, okay, through both the dopamine transporter on the cell membrane and also the vesicular monoamine transporter 2 on the synaptic vesicle membrane. Okay, so their mechanism is described as a reverse transport. So what I think the general viewpoint is that you will douse the axon terminal in the amphetamine drug. Okay, so now there's loads of amphetamine drug in the extracellular fluid, and then what seems to happen is the amphetamine drug is uptaken by the dopamine transporter. Okay, so it goes into the axon terminal via the dopamine transporter. Meanwhile, it seems that it will be taken up by the dopamine transporter in exchange for a dopamine molecule being thrown out from the cytoplasm into the extracellular fluid. So it seems that this is some sort of exchange where the amphetamine goes in through the dopamine transporter and then the dopamine molecule is thrown out. Okay, so that's what's meant by the reverse transport of the dopamine transporter, because it's now transporting dopamine in the reverse direction to the way it would have transported it originally. Now, not only is that throwing dopamine out, which is exactly what we said amphetamines were going to do, they were going to raise the dopamine level in the extracellular fluid, but it also gets the amphetamine molecule into the cytoplasm of the cell. And now the amphetamine molecule doesn't stop there. What it starts to go and do is it starts to go and mess around with the vesicular monoamine transporter 2 as well. It starts to go again into the synaptic vesicle lumen via the vesicular monoamine transporter 2 in exchange for a dopamine molecule being thrown out. Okay, so again it sets up this reverse transport system with the vesicular monoamine transporter 2. Okay, it will go in exchange for dopamine molecules coming out. So what appears to happen then is you douse your axon terminal in the amphetamine drug. Okay, it will then be transported in by the dopamine transporter. Meanwhile, every time you transport an amphetamine molecule in, the dopamine transporter starts transporting a dopamine molecule out. Okay? Sorry, did I say that right? Every time you transport an amphetamine molecule in, the dopamine transporter will transport a dopamine molecule out. In addition, the amphetamine molecule will then go and mess around with the vesicular monoamine transporter 2. It will again set up a reverse transport system where it will go into the synaptic vesicle lumen in exchange for a dopamine molecule going out into the cytoplasm. So this means you're going to firstly empty the synaptic vesicles into the cytoplasm, and then you're going to empty the dopamine out of the cytoplasm into the extracellular fluid by the dopamine transporter. So you set up reverse transportation through the dopamine transporter and the vesicular monoamine transporter 2, and that then leads to this massive release of dopamine into the extracellular fluid, okay, which was triggered by no action potential at all. Okay, so then you're going to get a large amount of dopamine released into the nucleus accumbens and medial prefrontal cortex, okay, and that's now the teaching signal that will then cause the remodeling of the brain, that's then going to cause cravings and wantings for the drug, and also the associative memories that are going to bind drug-associated cues to the initiation of drug-seeking behavior. Okay, right, so that then is the way that the amphetamines work. Okay, right, so what we're now going to turn our attention onto is two more drugs. Okay, we're going to turn our attention onto phencyclidine and then onto ketamine. Now, both of these are going to work in the same way as cocaine works, okay, but I would like to say a little bit more about both of them. Okay, right, let me get some more paper here. So, phencyclidine, firstly, I'd like to show you the structure of phencyclidine just to explain why it's called PCP for short. Okay, so phencyclidine is a shortened name already, but you can shorten it further to PCP. And you might be wondering, well, why is phencyclidine shortened to PCP? And the answer is it's not shortened to PCP. Okay, PCP is short for the full name of this molecule. Okay, and the full name of this molecule is 1, and then brackets, 1-phenyl cyclohexyl. Okay, so this is phenyl cyclohexyl. Okay, and then piperidine. So then close brackets, and then it's piperidine. So PCP is really short for the phenyl cyclohexyl piperidine portion here, rather than short for phencyclidine. So phencyclidine itself is a shortened name, basically, of phenyl cyclohexyl piperidine. Okay, right. So, I would like to talk you through this name. I can't show you a great big chemical name like that and then not talk you through the actual structure of this molecule. So, let's start off with what is piperidine. Okay, and then we'll come on to the 1,1-phenylcyclohexyl portion. Okay, so the structure then of piperidine is it's a 6-membered ring, okay, with a single nitrogen in. Okay, so again I'll show this through skeletal formula. So here is the nitrogen up here at the head of this ring, okay, and then we've got 5 carbons in this ring as well. 1, 2, 3, 4, 5. And all of the bonds in this ring are going to be single bonds, okay. Then off the nitrogen you're going to have a hydrogen, and I'm going to have to show that moreover on the skeletal formula. Off each of these carbons you'll also have 2 hydrogens, but I don't need to show that because this is a skeletal formula. Okay, so this is the structure of piperidine. Okay, that's that portion. Now, what are we going to stick on to piperidine? Well, off the first member of the piperidine ring, that's what this portion is here, okay, we are going to stick this 1-phenylcyclohexyl molecule. Okay, right, so firstly let me tell you what is the first position of a piperidine ring. Okay, well, it is this nitrogen. Okay, so this is the first position here. This thing here refers to the fact that we are going to stick something off this nitrogen. Okay, so what we're going to do then is we're going to remove the hydrogen that comes off this nitrogen, and we are going to stick a 1-phenylcyclohexyl group. Okay, so what is a 1-phenylcyclohexyl group? Okay, so cyclohexyl firstly. Cyclohexyl just refers to a cyclohexane molecule. Okay, like so. So that's just a 6-membered ring. Okay, where all of the bonds between the 6 carbons are single bonds, and then of course every single carbon will then have 2 hydrogens coming off. Okay, now to create 1-phenylcyclohexane, what we would have to do is just stick a phenyl group off. Now what is a phenyl group? Well, phenyl group refers to a benzene ring. Okay, so all we'd have to do then is stick a benzene ring off the cyclohexane ring to create 1-phenylcyclohexane. So this molecule here would be 1-phenylcyclohexane. Okay, and then it's not going to fit in, never mind. Cyclohexane. Okay, so it is this molecule that we are going to attach onto the nitrogen that comes off, well, the nitrogen here of the piperidine ring. Okay, we are basically going to take the hydrogen off this nitrogen, and we're going to take the hydrogen that's off this carbon here. Okay, of the 1-phenylcyclohexane. Okay, because remember this carbon has only got 3 bonds at the moment, so a final bond would be to a hydrogen. We're going to take that hydrogen off, and we're then going to bind this nitrogen to this carbon here. Okay, and the nicest way then to show the full structure of 1,1-phenylcyclohexyl piperidine is to put the cyclohexane then in the middle here, and then we'll have the 2 bonds going either way like so, and then we'll have the benzene ring or the phenyl group here sticking off like so. There it is. And then we'll have the piperidine ring on the other side, so that it's nice and symmetric in this way. So here's the nitrogen of the piperidine ring, and here are the 5 carbons of the piperidine ring. So this molecule is now Phencyclidine or PCP or 1,1-phenylcyclohexyl piperidine, whichever one you want to call it. Okay, so that's just a little bit of information about why it's called PCP. Okay, so how does PCP work then? Oh, and by the way, I should probably tell you its colloquial name. Okay, it's also colloquially referred to as angel dust. Okay, right, so how does this work to produce addiction? And remember, in the case of all of these addictive drugs, we are only looking at the mechanisms by which they produce addiction. We are not looking at the mechanisms by which they produce all of their other many effects. Okay, so how do they produce addiction? Well, they do the same thing as cocaine. They PCP blocks the dopamine transporter, okay, on the dopaminergic neurons, which are projecting into the nucleus accumbens and the medial prefrontal cortex, and hence you stop the reuptake of dopamine from the extracellular fluid by the axon terminals, okay, and that means that the dopamine that you release at a basal level is now going to have its signal amplified hugely, okay, so it's going to remain there for much longer. It's going to stimulate dopamine receptors in the medial prefrontal cortex and the nucleus accumbens much more, okay, and therefore you're going to induce this remodeling of the brain to produce craving and wanting for the drug molecule, and also the associations between drug cues and drug-seeking behavior. Okay, and therefore leading to the gradual addiction to the drug. Okay, right. Related is the molecule ketamine. Okay, and I'm not going to go through the molecular structure of ketamine. All I'm going to say about ketamine is that ketamine also blocks the dopamine transporter, just like phencyclidine and cocaine, okay, and this is how it's also going to produce addiction. Okay, so we've now seen 4 types of drugs, okay, that all produce addiction. We've seen cocaine, we've seen the amphetamines, okay, we've seen phencyclidine, and we've now seen ketamine, okay. What we're now going to move on to is something that's going to work in a totally different way to all of these 4, okay. We're going to move on to how cannabis works. So firstly, what I'm going to do is tell you about the active ingredient in cannabis, okay, and then what we will do is see how this is actually going to result in an increased amount of dopamine coming into the nucleus accumbens and medial prefrontal cortex. Okay, right, so what is the actual active ingredient within cannabis? Well, it is something known as tetrahydrocannabinol, okay, and for short, tetrahydrocannabinol is often abbreviated to THC. Okay, did I spell that right? I think so. THC for short. Okay, now, before going on to how tetrahydrocannabinol actually works, I want to explain something regarding the structure of tetrahydrocannabinol. Okay, so if you are seeing a NICE article, they will just refer to tetrahydrocannabinol as tetrahydrocannabinol. If you are instead reading a nastier article, they will refer, but more correct article, they will refer to the active ingredient of cannabis as delta-9, and then they'll put tetrahydrocannabinol. Or if you're reading a scrupulous article, okay, which is very, very correct, they will refer to the active ingredient of cannabis as negative trans delta-9 tetrahydrocannabinol. So negative trans delta-9 tetrahydrocannabinol, which I'll just abbreviate down to THC. Basically, the first thing I want to do is explain what firstly the delta-9 means, and then what the negative trans delta-9 tetrahydrocannabinol actually means. Okay, and it is truly, this is the active ingredient of cannabis. Negative trans delta-9 tetrahydrocannabinol is the actual active ingredient of cannabis. Often people will just say tetrahydrocannabinol, not to scare people, okay, but it's a little bit more ambiguous because there are other isomers of tetrahydrocannabinol other than this particular isomer, and it's this isomer, this specific isomer of tetrahydrocannabinol, that is the active ingredient of cannabis. Okay, right, so firstly let's explain the delta-9 portion, and then we'll come on to this negative trans portion. Okay, so I'm going to firstly show you the structure then of delta-9 tetrahydrocannabinol, and then we'll come on to the negative and the trans bit. Okay, so, right. So you start off with a 6-membered ring here, and of course I'm showing this structure in skeletal formula again, rather than molecular formula. Okay, so this is a 6-membered carbon ring here. You're going to have a double bond here, and you're going to have a methyl group coming off up here. Okay, then below this you're going to have another 6-membered ring joined here, but it's not going to be all carbons this time. You're going to have an oxygen right at the tip here. So here's an oxygen, and then off this carbon here you're going to have 2 methyl groups, one here and one here. Then finally you have another 6-membered ring, which is going to be a benzene ring here. Okay, so you have a double bond there, and a double bond there. Okay, and this is the structure then of delta 9 tetrahydrocannabinol. So what does the delta 9 refer to? Well, basically this double bond that I have put here, okay, this can move. Okay, it can be in different positions. Okay, it can't move in one molecule, but different forms of tetrahydrocannabinol will have this double bond in different positions. Okay, so if you see other numbers up there, delta something else, that will be telling you that this double bond will be in different positions. Okay, the position that I have drawn it in is the exact position that it will be in delta 9 tetrahydrocannabinol. Okay, this is the 9th carbon of the molecule. Okay, so that's why it's called delta 9 tetrahydrocannabinol. It's just referring to where this double bond is here. Okay, so in other forms of tetrahydrocannabinol where this number is different, you'll have the double bond somewhere else. So the one that's in cannabis has the double bond here. Okay, now the negative trans bit is more subtle. Okay, this is a bit which requires a little bit more understanding of organic chemistry. Okay, this is referring to optical isomerism of the molecule. Okay, so this molecule has multiple optical isomers. Okay, because you have 2 chiral centers. Okay, so let me firstly show you where the chiral centers are. You might like to try and find the chiral centers for yourself. Okay, so the chiral centers are here and here. Okay, so a chiral center is just a carbon which has 4 different groups attached to it. Okay, and that results in it having two possible structures, basically, 2 possible structures that are distinct. Okay, so this is a chiral center here. Both of those are chiral centers because they have 4 separate groups coming off. Even though in my picture it looks as though they only have 3 different groups coming off, you have to remember there's a hydrogen coming off each of those, which takes it up to 4. Okay, so basically if we now put in the hydrogens here, okay, if we I'm just wondering when I'm going to have to draw this again. I'll draw it zoomed in here. Okay, so this is this portion here, that's that arch up there, the top of this ring here, and then we're going to have this carbon here. Now, imagine that this carbon here, we're going to have to imagine in 3D. Whenever you're doing anything with optical isomerism, you have to imagine in 3D, not 2D. Okay, so imagine that this carbon right at the center here is in the plane of the piece of paper. Okay, so that we can do that. We can put that atom in the plane of the piece of paper. We're then going to put this one here in the plane of the piece of paper, and this one here also in the plane of the piece of paper. Okay, so I'm going to arrange this molecule so that this one, and this one are all in the plane of the piece of paper. I cannot then get this one in the plane of the piece of paper, okay, because the 2 remaining bonds that are coming off this carbon, one of them needs to come out of the page at an angle like that, okay, the other needs to be going into the page at an angle like that. Okay, so we've got 2 more bonds coming off here. We've got a bond to this carbon here, and we've got a bond to the hydrogen as well. Now, you can either have the carbon coming out of the page towards you and the hydrogen going into the page away from you, so I'll show that first. Okay, so the way that I show bonds, and it's not just me, the way that commonly people show bonds coming out of the page towards you is by making them get thicker as you go along. Okay, so this is a bond coming out of the page towards you. Okay, so the carbon that's coming off this carbon here, so this carbon here we're talking about, will be coming out of the page towards us, and then the hydrogen, which I'm now going to show, so I'm going to break my skeletal formula, okay, will be going into the page away from us, and the way that you show this is by a dashed line like so. So this would be the hydrogen here, and this would then be the carbon. Okay, so that's one way you could do this, or you could do it the other way round. Okay, now, the negative portion of this means that the hydrogen is going into the page away from us. Okay, so if the hydrogen goes into the page away from us on this specific carbon here, then that will be the negative isomer of this molecule. If instead we did it the other way round and we had the hydrogen coming into the page, out of the page towards us, and the carbon going, whoops, not like that, and the carbon going out of the page, going into the page away from us, then that will be the positive isomer. Okay, now you then have to consider also the fact that this carbon here also is a chiral center. Okay, so again, if we imagine we're talking about this carbon here, this is this one here. If we imagine that this carbon is in the plane of the piece of paper, which we already have done, okay, and then we imagine that we put this carbon down here also in the plane of the piece of paper, then the two final bonds coming off this carbon, one to this carbon here and the other to a hydrogen atom, one of them will be coming out of the page at an angle like this, and one will be going into the page at an angle like this. Okay, so we can imagine, if you like, that the hydrogen will come out of the page towards us and the carbon will go into the page away from us. So let's show this. So here's the carbon going into the page away from us, and then we'll have the hydrogen coming out of the page towards us with this bond that gets thicker towards the end. Okay, but again, you could have it both ways round. Okay, now, where does this trans come from? This says that the hydrogen here is going to be on the opposite side to the hydrogen here. Trans means on the opposite side. Okay, so trans, on the opposite side, on the opposite side. Okay, so in this case, what's going to happen is the hydrogens are going to be on opposite sides. In this bond here, the hydrogen's going into the page away from us, and on this side, the hydrogen's coming into the page, is coming out of the page towards us. So this hydrogen is going to be going into the page, this one's going to be coming out of the page, so they are on the opposite sides basically. If on the other hand this hydrogen was going into the page away from us and the carbon here was coming out of the page towards us, then this hydrogen and this hydrogen would be on the same side, and then it would be called the cis isomer. So I have shown you here the optical isomerism of negative trans delta 9 tetrahydrocannabinol. Okay, this one first is in the negative state, okay, and then this one is in the opposite side to the hydrogen here, okay, and therefore it's the negative trans delta 9 tetrahydrocannabinol. Okay, so basically there are 4 different optical isomers of delta 9 tetrahydrocannabinol. Okay, you can start with this hydrogen going into the page away from us and this carbon going out of the page towards us. That will be the negative isomers. Okay, you then have to make your decision about this one here. Either the hydrogen can go into the page away from us and the carbon can come out of the page towards us, in which case the hydrogen will be going in the same direction as the hydrogen here, and that will be the negative cis isomer of delta 9 tetrahydrocannabinol, or this hydrogen can come out of the page towards us and this carbon can go into the page away from us. That will be the negative, and now it's trans isomer. Okay, then you switch over to having this one in the positive form. Okay, so now we'll go over to the positive isomers. The hydrogen is now coming out of the page towards us here, and the carbon will be going into the page away from us. Okay, and now if the hydrogen comes out of the page towards us and the carbon goes into the page away from us off this carbon, then these two hydrogens will be on the same side, so that will be the positive cis isomer. And then if the hydrogen goes into the page away from us off here and the carbon comes out of the page towards us, then they'll be on opposite sides now, and that will be the positive trans isomer. Okay, right, and those are the 4 optical isomers of delta 9 tetrahydrocannabinol. Okay, so that is what this negative trans delta 9 tetrahydrocannabinol refers to. It refers to the specific optical isomerism of these 2 chiral centers here. Basically, off this one here, this carbon will be coming out of the page towards us and the hydrogen will be going into the page away from us. Okay, and then off this one here, it will be in the opposite way. So this carbon will be going into the page away from us, and then the hydrogen will be coming out of the page towards us, and that's in negative trans delta 9 tetrahydrocannabinol. Okay, so that I hope has just cleared up what those accessory words on the front of tetrahydrocannabinol actually mean. Okay, from now on we will, I think, abbreviate it down to delta 9 tetrahydrocannabinol. We'll go halfway in between, basically. Okay, so this specifically is the optical isomer of delta 9 tetrahydrocannabinol that is found within cannabis and is the main active ingredient of cannabis. Okay, right, so we now want to discuss how then how does tetrahydrocannabinol, how does it actually produce addiction? Okay, and again it's going to work by increasing dopaminergic transmission in the nucleus accumbens and the medial prefrontal cortex. Okay, but it's going to do it by a very different mechanism to the psychostimulants that we've seen, and also phencyclidine and ketamine. Okay, it's going to work on the level of the ventral tegmental area, so we need to look at a very different portion of the dopaminergic neurons now. Rather than looking at their axon terminals, we need to go back and look at the cell bodies of the dopaminergic neurons. Okay, and what is controlling how much they fire? Okay, right. So let's say that this is our dopaminergic neuron sitting in the ventral tegmental area. Okay, so here it is. This is its axon going off in the medial forebrain bundle to the nucleus accumbens, or the medial prefrontal cortex. Okay, now this dopaminergic neuron will have a huge number of dendritic spines all over its dendrites, okay, and these will be collecting information from other neurons about whether the dopaminergic neuron should fire or not. Now basically there are a huge number of neurons whose job it is to inhibit this dopaminergic neuron and stop it from firing. Okay, so let me put one of these neurons on here. Okay, like so. So this is going to be one of these GABAergic neurons. Okay, it's going to be releasing the inhibitory neurotransmitter GABA. So this is what's known as a GABAergic inhibitory interneuron. Okay, and it's going to be inhibiting the dopaminergic neuron of the dopaminergic neuron of the ventral tegmental area. Okay, so this is the interneuron. Okay, right. So basically, this GABAergic inhibitory interneuron will be firing, and it will be releasing GABA onto the dendritic spine of this dopaminergic neuron here. Okay, and that GABA will be opening GABA A receptors, which we'll see more later, which will be allowing chloride anions into the cytoplasm of the dopaminergic neuron. Okay, and this will be making it less likely that the axon hillock over here actually fires an action potential. Okay, and this is what's stopping the dopaminergic neurons from firing too rapidly. Okay, so you've got loads of these GABAergic inhibitory interneurons synapsing onto the dopaminergic neuron and suppressing its firing. Okay, right. Now, on the axon terminals of these GABAergic inhibitory interneurons, you have receptors for tetrahydrocannabinol, or at least receptors that tetrahydrocannabinol can work on. Okay, now this receptor is going to be a G protein coupled receptor. So again, it's going to have this characteristic structure where you have 7 membrane spanning alpha helices, like so. And this specific receptor that tetrahydrocannabinol is going to work on is known as the CB1 receptor, okay, standing for cannabinoid 1 receptor. So the C is for canna, and then the B for binoid. So the cannabinoid 1 receptor. Okay, so let's colour in this cannabinoid 1 receptor in red here. Okay, so delta 9 tetrahydrocannabinol, the active ingredient of cannabis, is going to work on this cannabinoid receptor 1, okay, and it's going to activate it, okay, on these GABAergic neurons. So I want to stress we're not talking about the dopaminergic neuron. The cannabinoid receptors aren't on the dopaminergic neuron, they're on the GABAergic neuron, okay. Specifically, they're on the axon terminals of the GABAergic neuron. And when this cannabinoid 1 receptor becomes active on the axon terminal, it is going to inhibit the release of GABA. Okay, so it's going to inhibit the release of GABA. Okay, which means that now the amount of GABA that this axon terminal will release every time the axon fires an action potential is going to be smaller. Okay, so you're going to now release less GABA. Okay, right, and that means that the amount of inhibition that this neuron, this dopaminergic neuron, is receiving is going to go down. Okay, that's going to mean that we're going to swing the balance between the excitatory inputs that this dopaminergic neuron is receiving and the inhibitory inputs that this neuron is receiving. Okay, so that this neuron now receives far fewer inhibitory inputs, and therefore it's going to be far easier to stimulate. So excitatory inputs that now previously wouldn't have managed to produce action potentials will. So this neuron is going to end up firing action potentials far more rapidly, and therefore you're going to get more dopamine being released into the nucleus accumbens and the medial prefrontal cortex. So basically, it all comes down to the fact that if you want to make the neuron fire at a faster rate, you can either increase the amount of excitatory input to the dopaminergic neuron to swing the neuron in favor of firing action potentials, or you can leave the excitatory input alone and then decrease the inhibitory input, and that will again make it more likely to fire action potentials. Okay, and we here have decreased the inhibitory input by activating these cannabinoid 1 receptors on the axon terminals of these GABAergic inhibitory interneurons. Okay, right, so we'll call it there for this video. In the next video, what we will talk about is the benzodiazepines, okay, which are anxiolytic drugs also used as hypnotics, okay, that also have mildly addictive properties, okay, and these are also going to be interfering with these GABAergic inhibitory interneurons.